All right, so today we're going deep on something pretty amazing.
Yeah.
The cosmic microwave background.
CMB.
It's basically like the universe's baby picture,
Mm-hmm.
but it also tells us how the universe is structured, how it evolved, all this crazy stuff.
Yeah.
And you guys send in some fascinating articles about it.
Yeah, some great stuff out there.
Really, really interesting stuff.
Yeah, the CMB, it's basically this faint afterglow of radiation
Okay.
that's left over from the Big Bang.
Wow.
A snapshot of the universe when it was just 380,000 years old.
So we're talking about the oldest light we can see.
The oldest light, yeah.
That is just wild. And it's all around us.
It is.
You can even see a tiny bit of it as static on old TVs.
That's right. Yeah, you can.
That's so cool.
So by studying the CMB, we can actually unlock secrets about the universe's origins.
Okay.
Its composition, how it's changed over billions of years.
It's like a cosmic time capsule.
It is. It's amazing.
So let's rewind way back to the beginning, before the CMB.
Right.
What was the universe like?
So imagine a universe that is incredibly hot and dense.
Okay.
Just a chaotic soup of particles like electrons and protons and photons constantly colliding with each other. And it was so dense that light couldn't even travel freely.
So the early universe was kind of like a cosmic mosh pit.
Yeah, that's a great way to put it.
Not exactly a place you want to hang out.
No, not at all.
So how did we get from this crazy mosh pit to the universe we know today?
Well, as the universe expanded,
Okay.
it cooled down.
All right.
And that cooling led to a pivotal moment that we call recombination.
Recombination.
Yeah, so this is when the universe cooled enough for protons and electrons to combine
Okay.
and form neutral hydrogen atoms.
So things started to settle down a bit.
Yeah, exactly. And this is where things get really interesting because before recombination,
Yeah.
the light was constantly bumping into those charged particles, getting scattered every which way. But when these neutral hydrogen atoms formed, the universe suddenly became transparent.
Oh, wow.
The photons were free to travel across the cosmos.
So it's like the universe flipped a switch and said, let there be light.
Yeah, you could say that.
And that first light, that's what we see as the CMB today.
That's exactly it. That first light has been traveling through space for billions of years.
Wow.
Stretching and cooling as the universe expands.
So it's gotten stretched out
Yeah,
over billions of years.
billions of years.
And now we see it as this faint microwave radiation.
That's right.
The CMB.
The CMB.
Okay, so we have the snapshot of the early universe.
We do?
But how do we actually read this snapshot?
Right.
I mean, it's not like a photograph we can just look at.
No, it's not. It's more like a cosmic code that we need to decipher.
Okay, the cosmic code.
Yeah. And one of the most fascinating things is that the CMB isn't perfectly uniform.
Okay.
It has these tiny temperature variations, these hot and cold spots.
Temperature variations, what do those tell us?
Those variations actually correspond to density variations in the early universe.
Okay.
So areas that were slightly denser show up as slightly colder spots in the CMB.
So how does that work?
Well, think of it like looking at cake batter before it's baked.
Mm-hmm.
You can see where the chocolate chips are clustered, right?
Yeah.
That gives you a clue about what the final structure of the cake is going to be.
Okay, I see what you mean.
The CMB is kind of like that. It's showing us where matter was clumped together in the early universe.
So those tiny temperature differences are essentially the blueprints for the entire universe.
That's a great way to put it. Yeah, they acted as seeds for the formation of the large-scale structures that we see today.
Wow.
Like galaxies and galaxy clusters.
That's just mind-blowing.
It is, and you know what?
What?
This incredible discovery
Yeah.
was made completely by accident.
I love a good science discovery story.
Me too. So back in 1965,
Okay.
these two scientists, Arno Penzias and Robert Wilson,
Mm-hmm.
they were working with this giant antenna,
Okay.
trying to eliminate all the sources of noise they were picking up.
So they were cleaning up their cosmic inbox, so to speak?
Exactly. They just wanted to get rid of the static so they could do their research.
Makes sense.
But there was this persistent hum they just couldn't get rid of,
Uh-oh.
no matter what they tried. And it turned out that this hum was actually the faint whisper of the CMB.
They had stumbled upon one of the most important discoveries in cosmology.
They did, and it earned them a Nobel Prize in physics.
Wow.
And it opened up this whole new window into the early universe.
That's remarkable.
It is.
So this accidental discovery revolutionized our understanding of the cosmos.
It really did.
Okay, so let's get into the nitty-gritty here.
Right.
What exactly does the CMB tell us about the universe's vital statistics?
Well, for starters, it tells us the age of the universe
Okay.
with remarkable precision. 13.8 billion years old.
13.8 billion years. That's a number that's hard to even wrap your head around.
I know, it's incredible.
And it's not just the age.
No.
The CMB also tells us about the composition of the universe.
It does. By analyzing the patterns in the CMB, we can figure out the proportions of ordinary matter, and dark energy.
Wait, dark matter and dark energy?
Yeah.
Those are some pretty big mysteries.
They're some of the biggest puzzles in cosmology.
I've heard of them, but I have to admit I'm a little fuzzy on the details.
Well, the CMB provides crucial evidence that they exist.
Really?
Yeah.
And that's where things get even more fascinating.
It does. It really does.
So the CMB, it's giving us clues about this mysterious stuff called dark matter and dark energy.
It is.
I mean, what's the connection there?
Well, let's start with dark matter.
Okay.
We can't actually see it directly.
Right.
It doesn't interact with light the way that ordinary matter does.
But we know it's out there.
We know it must exist.
Right, because of its gravitational effects.
Exactly. And those effects are actually visible in the CMB.
Okay, so how does the CMB reveal something we can't even see?
Remember those temperature variations we talked about?
Uh-huh. The hot and cold spots?
Yeah. So the patterns of those fluctuations are actually influenced by the presence of dark matter.
Okay.
Its gravity would have pulled matter together in the early universe,
Right.
creating these denser regions that show up as colder spots in the CMB.
So even though we can't see dark matter, it left its fingerprints on the CMB.
Exactly. It's like a cosmic detective story.
I love it.
And it's not just about the distribution of those spots.
Okay.
The specific pattern of the temperature variations, what we call acoustic peaks.
Acoustic peaks.
Yeah, they also provide evidence for dark matter.
Okay.
So these peaks tell us about the way that sound waves traveled through the early universe.
Hold on, sound waves in the early universe.
Yeah, I know it sounds strange.
It does.
But remember, the early universe was this incredibly hot, dense plasma.
Right.
Sound waves could actually propagate through this plasma, much like sound waves travel through air here on Earth.
Okay, so by studying the imprint of these sound waves on the CMB,
Exactly.
we can learn a lot about the universe's composition.
Including the amount of dark matter.
Wow, okay, so the CMB is helping us understand this invisible stuff called dark matter.
It is.
But what about dark energy?
Right, dark energy.
How does that fit into the picture?
Dark energy is even more mysterious.
Okay.
It's this force that's causing the universe's expansion to accelerate.
To speed up.
Yeah, and while we don't fully understand what it is, the CMB provides evidence that it exists.
So how does the CMB tell us about something as elusive as dark energy?
It's all about the geometry of the universe.
Geometry.
Yeah, so by measuring the precise size and shape of those temperature fluctuations in the CMB,
Okay.
scientists have been able to determine the overall curvature of the universe.
Curvature. So is the universe, like, curved?
Well, it turns out the universe is remarkably flat.
Flat.
Flat, yeah. And that means that parallel lines will always remain parallel,
Okay.
unlike in a curved universe, where they might converge or diverge.
So the universe is flat like a pancake.
Well, not exactly.
No.
It's more about the geometry of space itself.
Yeah.
But the point is, for the universe to be flat, there needs to be a certain amount of total energy within it.
Okay. I think I'm following so far, but where does dark energy come in?
Well, here's the thing. The amount of matter that we can observe,
Okay.
both ordinary matter and dark matter,
Uh-huh.
it's just not enough to account for that critical energy density needed for a flat universe.
So there's a missing piece to the energy budget.
Exactly. And that missing piece is dark energy.
Uh-huh.
Dark energy acts like this negative pressure.
Negative pressure.
Yeah, pushing everything apart and causing the universe's expansion to speed up.
Wow. So even though we don't know what dark energy is, the CMB is giving us strong hints that it's out there.
It is. And it's playing a huge role in shaping the universe's destiny.
That's pretty amazing.
It is. It's like this cosmic mystery novel
Okay.
with some key pages missing.
Yeah.
But the CMB is giving us enough clues to piece together a pretty compelling story.
You know, it's just incredible, all this talk about dark matter, dark energy, and the early universe really makes you appreciate the sheer scale and the mystery of it all.
I know, it really is awe-inspiring.
And it's amazing that we can even study these things, all thanks to this faint glow of radiation left over from the Big Bang.
It really speaks to the power of science and how everything's connected.
So what's next for CMB research?
But one of the bigger questions is about this period called inflation.
Inflation.
Yeah, which is thought to have happened in the first fraction of a second after the Big Bang.
Okay, I've heard that term thrown around, but I'm not really sure what it means.
So inflation theory says that the universe went through this period of extremely rapid expansion in its very first moments.
Like blowing up a cosmic balloon really fast?
Yeah, that's a good analogy.
Okay.
So in an incredibly short amount of time, the universe grew from something unimaginably small to roughly the size of a grapefruit.
Wait, you're saying the entire universe went from something tiny to the size of a grapefruit in a fraction of a second?
That's the idea.
My brain is having a hard time processing that.
I know it's a mind-bending concept, but it explains a lot of what we see in the CMB.
Okay.
Like why it's so uniform on large scales.
Hmm.
You see, if the universe had always been expanding at the same rate,
Okay.
there wouldn't have been enough time for different regions of the early universe to come into thermal equilibrium.
Meaning
They would have had time to reach the same temperature.
Right.
But the CMB shows us that the early universe had this remarkably uniform temperature, suggesting that something must have happened to connect those different regions very early on.
So inflation, this rapid expansion theory,
Yeah.
it helps explain why the CMB is so uniform.
Exactly.
But how does the CMB actually help us study something that happened so long ago?
Well, inflation would have left behind this unique signature in the CMB's polarization.
Polarization.
Yeah, polarization is basically a way of describing the orientation of light waves. Think of it like polarized sunglasses, which only allow light waves vibrating in a certain direction to pass through.
Right?
In the case of the CMB, the polarization pattern can tell us about the gravitational waves that were generated during inflation.
So we're basically looking for the faint whispers of inflation imprinted on the CMB.
Exactly. It's like cosmic archaeology.
It's incredible, and if we find those whispers,
It would be huge.
it'd be a major breakthrough in our understanding of the very first moments of the universe.
Absolutely. And there are a number of experiments and telescopes that are actively searching for these polarization signals in the CMB.
Wow, so this is a very active area of research.
It is very exciting.
That's so cool. It's amazing to think that the CMB might hold the key to unlocking some of the biggest mysteries about our cosmic origins.
It really is.
I'm definitely going to be following those experiments closely.
Yeah, you and me both.
Yeah.
It's a treasure trove of information.
It is a treasure trove.
And the more we study it, the more we realize just how interconnected everything in the universe is.
Yeah, from the smallest particles to the largest structures. Exactly.
You know, it's just amazing how much we can learn about the universe from something as simple as this faint afterglow of radiation.
It is. It really speaks to the power of science and how everything's connected.
Yeah, and we started this deep dive talking about the CMB being like the universe's baby picture, but it's so much more than that.
It is. It's like a blueprint, a time machine, a cosmic detective story.
All rolled into one.
Yeah, and the best part is the story is still being written.
Right.
The more we learn about the CMB, the more we realize how much we don't know.
It's like we're standing at the edge of this vast, uncharted cosmic ocean, and the CMB is our beacon.
I like that. Yeah, guiding us deeper into the unknown.
In this journey of cosmic exploration, it's not just for scientists, you know?
Oh, it's not.
It's something we can all be a part of.
Absolutely.
I mean, anyone can look up at the night sky and feel a sense of wonder.
Yeah.
But knowing that there's this faint afterglow of the Big Bang all around us, that we can even detect a tiny bit of it on our old TVs.
It just adds a whole other level of amazement.
It really does. It connects us to the universe's earliest moments.
Right.
Through this ancient light.
So for anyone listening who wants to learn more about the CMB, what resources would you recommend?
Oh, there are so many great resources out there.
Yeah.
NASA's website is a great place to start. They've got incredible images,
Okay.
explanations for non-experts, even some interactive tools.
Cool.
And if you're looking for a deeper dive,
Right.
there's this classic book called The First 3 Minutes by Steven Weinberg.
Okay.
Explores the early universe in fascinating detail.
Cool. And I know there are tons of documentaries and articles and videos online.
Oh yeah, countless resources that break down the science in a really accessible way.
Perfect. Well, we'll be sure to include links to some of those resources in the show notes for anyone who wants to explore further.
Right.
This has been an amazing journey exploring the CMB with you.
It really has.
It's incredible to think that something as simple as leftover radiation from the Big Bang can tell us so much about the universe.
It's mind-blowing.
Its past, present, and even its future.
It really is, and the journey continues.
It does well. On that note, we'll wrap up this deep dive into the cosmic microwave background.
Sounds good.
But before we go, I want to leave you with one final thought.
Right.
We've talked about the CMB as this incredible cosmic time machine,
Mm-hmm.
a way to look back at the very beginning of the universe.
Right.
But what if it's also a key to understanding our future?
Hmm.
What if hidden within those faint temperature fluctuations are clues about the ultimate fate of the universe?
That's a great question.
That's something to ponder as you gaze up at the night sky.
It is.
Until next time, keep exploring